You're watching me right now thanks to synthetic fertilizers that make billions of lives possible with readily available nutrients like nitrogen needed for amino acids, DNA, and chlorophyll. But even though nitrogen is a majority of the air we breathe, nitrogen in the atmosphere only exists as N2. N2 has a triple bond, one of the strongest atomic bonds. The Haber process helps us by converting N2 into ammonia, which is easier to use and vital for those fertilizers. For every N2 and 3H2, we can yield 2 NH3. But sadly, the reaction's thermodynamically unfavorable. An iron catalyst can lower the activation energy, but even this isn't enough. To make this impossible reaction happen, we need to call in Gibbs free energy, or the energy available to drive the reaction. But how Gibbs feels about the reaction depends on the moods of her friends, enthalpy and entropy. Change in Gibbs free energy equals change in enthalpy minus temperature times change in entropy. For the reaction to occur, Gibbs free energy must be negative to fire her up. Under the high temperature required by the catalyst, enthalpy must be negative, and entropy must be positive to keep the other two in check. Enthalpy here is negative 46 kilojoules per mole. But wait, entropy is negative 2 since particles decrease. 4 reactant molecules versus 2 product molecules. Gibbs ends up the positive peacekeeper and she won't favor the reaction. It sounds like a dead end for the trio, but we can get them on the right page with Le Chatelier's principle, which tells us if the pressure of the reactants increases high enough, the reaction will yield ammonia. Going from 4 molecules to 2, even with negative entropy, accommodates for increased pressure, shifting the reaction towards products. Decreasing the molecules lowers its pressure and gives us that ammonia. Our environments influence all of us, from our friends to enthalpy, but under the right pressure, we are all possible.